Today, let us get introduced ourselves to redox titrations. As we all know that titrations can be studied by visual methods as well as by instrumental methods. Today, we shall learn about visual method and we shall talk about redox indicators and their working. So, let us go on with redox titrations. Basic principle. As we all know that in redox titrations or in any redox reaction, electrons are given and taken. Here the titer solution and titrant solution give and take the electrons. An oxidizing agent takes up electron from reducing agent and vice versa. The tendency to donate or accept the electrons is relative in every case. It is different in different reactions. A common example studied for redox titrations is here. It is ferrous solution reacting with ferric solution and the ferrous ions get converted into ferric ions and ferric ions get converted into ferrous ions. By visual method, when the redox titration is studied, the indicators used are called as redox indicators, and by instrumental methods, when the redox titrations are studied, they are studied by potentiometry. Potentiometry well explains the redox titrations. Here is a common construction, a potentiometer and the cell constituting two electrodes. One of the two electrodes in this cell is usually a standard electrode and another which contains the titer solution is named as indicator electrode. The titrant is there in the burette. The standard electrode is commonly a saturated calomel electrode whose potential is constant and is equal to 0.242 volts. So, as titration proceeds, this titer solution gets consumed. Here, the solution concentration of the solution changes. This reflects in its electrode potential. So, the change in EMF of cell is due to change in electrode potential of the indicator electrode only. The total reaction reflects its EMF is titled as E system. So in all we can say that change in E cell is corresponding to the change in E indicator which corresponds to the change in the electrode potential of the system. What the system constitutes? Initially there is titer solution present in excess because whatever amount is delivered from the burette or the titrant solution gets consumed by the titer, hence it is present in excess. So potential of the system corresponds to the titer solution itself. So the platinum electrode placed in this solution delivers the potential of titer solution before equivalence point. At equivalence point, all the species exist at a definite concentration. So E system is composed of both the electrode solutions, that is titer and titer electrode solutions, and after equivalence point titrant is present in excess. So E system corresponds to the electrode potential constituted by the titrant solution. We shall talk about the potentiometric calculation or EMF calculation in the next part, and here we shall talk about the visual titrations, and visual titration requires the indicator. What are the indicators and how do they work is studied in this part. The redox indicators are organic compounds and these compounds show different colors in different states of oxidation. That is, in oxidized form they are having different color, whereas after accepting electron they get reduced, and in reduced condition they show a different color. So let us find out what happens to the potential of the indicator, because totally what is changing in the redox titration is potential of the indicator electrode or potential of the titrant solution. So indicator along with the titer changes its color. How does it change its color? So we shall study the change in EMF delivered by the indicator. So that is equal to, by the Nernst equation, standard electrode potential E0n minus the usual factor 0.05916 divided by n, and log of the ratio reduced species concentration divided by oxidized species concentration. As seen in the equation, the standard electrode potential is usually a constant. This factor is constant when n is constant, that is for the same indicator it is the same, and log of this ratio. Look at this ratio. If we want to find the distinct color change, one color changing to another, the concentration of one species must be 10 times more than another species. So this ratio has to be either 10 or greater than 10 or less than or equal to at least 1 upon 10. So if we substitute this condition in this equation, then it becomes log of 10 or log of minus 10, that is equal to plus 1 or minus 1. So this factor in a way becomes constant in this fashion. Indicator potential equal to standard electrode indicator potential minus this factor. So when n is equal to 1, then this factor is equal to 0.0592. So E indicator is nothing but indicator potential minus 0.0592. If n is equal to 2, then this factor becomes 0.18 volts to see the color change distinctly. So at equivalence point, this much change in potential should happen to show the color change when n is equal to 1, and this much change in potential must happen to show the color change when n is equal to 2, that is number of electrons transfer during this reaction is equal to 2. Here are some examples of redox indicators. These two, that is ferroin and diphenylamine sulfonic acid, we are going to study in detail. The transition potential of ferroin is 1.06 and that of diphenyl sulfonic acid is 0.84 as given in the reference books. Let us see the traditional diphenylamine indicator. We have diphenylamine solution provided in our laboratory. We take a few drops of them and add to the titer solution. What happens to the indicator? Let us see theoretically. This is our diphenylamine. It gets irreversibly converted into diphenylbenzidine. This is also of say greenish color. This diphenylbenzidine reversibly gets converted into diphenylbenzidine violet by losing 2 electrons and 2 protons. This is the color change, or this is the transition reaction which takes place at 0.76 volts. There are some typical things about diphenylamine. First of all, it is not soluble very greatly in water. So being less soluble, its sulfonic acid derivative is used which is quite soluble in water. What we do is we prepare diphenylamine solution in concentrated sulfuric acid, which prepares its derivative in the solution itself. Then the transition takes place, the transition potential gets converted from 0.76 to 0.85, increases a bit. Third point is this indicator forms insoluble tungstate and becomes useless if a tungsten compound is present in the sample. So for such samples, diphenylamine cannot be used as indicator. It is commonly used for Fe2 plus versus potassium dichromate solution titration. This is estimation of Fe2 plus usually done by dichromate using diphenylamine indicator, whereas we ask to add orthophosphoric acid in adequate amount. What is the function of orthophosphoric acid? It forms a stable colorless complex with these Fe2 plus ions. The advantage of complex formation is that it decreases the equivalence point potential and brings it to about 0.95 volts, which reduces the titration error. This is another one, Ferroin. The long name is iron 2 orthophenanthroline. It is phenanthroline. This triplet, 3 benzene rings along with 2 nitrogen in the ring. This part is called as phenanthroline. This reacts with Fe2 plus, forming this big complex. This big complex may get oxidized, that is only Fe part gets oxidized to Fe3 plus. These two colors are different. This is pale blue in color, this is red in color. This transition takes place at 1.06 volts. Another some characteristics of ferroin. In the titration of Fe2 plus versus steric, when there is little addition of 0.1 ml around equivalence point, the shaft in potential, the sudden change in potential is equal to 1.28 to 0.931 volt. This change can include 1.015 in between. So ferroin indicator is quite suitable to locate the equivalence point of Fe2 versus Ce4 titration. The concentration of indicator required is very low. It is 1 into 10 raised to minus 5 molar. This is the way to think of choice of indicator. This is the graph of EMF versus volume of steric solution added. Look at the equivalence point. Equivalence point is 1.06. It is more than 1. So if we use diphenylamine indicator for steric titration, then the diphenylamine indicator will change its color much before the equivalence point commences, whereas ferroin will change its color during the equivalence point, 0.1 ml with less than 0.1 ml accuracy itself. So this way we choose the indicator that the color change transition should be corresponding to the potential transition at equivalence point. This is the potential before equivalence point, slightly more than 0.8 and up to 1.4. So if our indicator changes its color below this vertical line or above beyond this vertical line, then this indicator will not be suitable for us, but the indicator must change its color during this transition potential itself. This is the way to choose the indicator for any titration. This is all about the redox indicators. We shall think of potentiometric application, how the potential changes during redox titration in part 2. Thank you.